Hi, my name is Liberty Schmidt, and this video will hopefully break down rate laws so that you can easily do these problems on your test or any occasion. So first, what is a rate law? Well, a rate is the change in X over time. So rate is change in concentration of a reactant over time. So just think of your X as being the concentration. Remember, from this point on, concentration will be shown by the element or compound being put in brackets. Next, let's talk about the units for this rate. Usually you'll see the units as one of the following. Just remember that the unit will be molarity and you are dividing it by time. Next, we need to see how to determine the rate based on a reaction. Take the example reaction shown. The rate would be what's below, with the lowercase letters equaling moles. Therefore, to find the rate, you take the change in concentration over time and multiply it by 1 over the moles of that substance. If you remember from previously in the year, reactants are normally subtracted from the equations. That is why the reactants for rates are negative and the products are positive. So now that we have a foundation for rate in general, we can move on to the rate law. So let's take a look at the reaction shown. Its rate law would be that rate equals the concentration of A to the M times concentration of B to the N times concentration of C to the D, where K is known as the rate constant. It's good to note, however, that the coefficients do not have a direct correlation to the exponents in the rate law. Also, the most important thing to remember is that the rate law must be experimentally found, meaning someone has to physically be in the lab determining what the rate law is for a reaction. You cannot just look at the reaction and know what the rate law is. So what do the exponents stand for in the rate law? They describe the order of the reaction, and the sum of the exponents are known as the overall order of the reaction. There are 3 types of orders that you will be dealing with in general chemistry: first order, second order, and zero order. A first order is when the exponent is 1, second order is when it's 2, and zero order when there is no concentration shown for that substance. Next thing we'll cover is what the rate does when you change your concentration within the rate law. Let's look at a first order to start. So let's think. The rate law for a first order reaction is rate equals K times the concentration of A. So rate is directly proportional to the concentration, since the concentration is only being raised to the first power. Therefore, if the concentration of A were to double, then so would the rate. Or if the concentration were to triple, then the rate would triple too. They are directly proportional. Next, we'll look at a zero order reaction. So, for a zero order reaction, rate equals K. There are no concentrations involved because the exponent is 0, and anything raised to the power of 0 is 1. So if there is no concentration in the rate law, then how is the rate law affected by changes to the concentration? Well, it isn't. There is no relationship between concentration and the rate of a zero order reaction. So if you double the concentration, or even multiply it by 100, the rate is going to stay constant regardless. Finally, we have the second order reaction. So the exponent on a second order reaction is 2. So this means that the rate is directly proportional to the square on the concentration. So whatever number you multiply your concentration by, the square of that will be what you multiply your rate by. For example, let's say you double the concentration, so you're going to multiply it by 2. This number squared is 4. So you would multiply your rate by 4. What if you triple it? You would be multiplying your concentration by 3. That squared is 9, so you multiply the rate by 9. This works no matter what you multiply your concentration by. Just remember that whatever the concentration is multiplied by, the square of that is what you multiply your rate, since it is a second order reaction. The last thing to cover is K, the rate constant. So you have to have a K in every rate law. Also, each rate law has to have a specific K. Another thing to note is that since it is a constant, K is independent of the reaction concentrations, meaning you can do whatever you want to the concentrations and your K will not change. However, your K can vary with temperature, so be on watch out for that. Then we have the units for K. Dr. Rogers put it best when he said that K will take whatever units it needs. To understand, let's think about a rate law in terms of just units. You have the rate, which is always molarity over time. Then you have your concentrations, which will always be molarity. So K has to be a unit that will cancel anything extra in the concentrations to get the desired unit of molarity over time. Let's look at this with our order of reactions. First order, we have our units of concentration equaling just 1 molar. Our desired unit is molarity over time. So the unit of K has to be 1 over seconds. This is because once you multiply your 1 over seconds times molarity, you get molarity over seconds, your unit for rate. For second order, you have a unit of moles per liter squared for your concentrations. You want to get to moles per liter per second. Therefore, we need to get rid of one of the moles and include time. So our K needs to be 1 over seconds times moles per liter. This will get us to our needed unit for rate. Finally, we have a zero order. We don't have any concentrations for this reaction. All we know is that our rate unit has to be molarity over seconds. This equals K. Therefore, our unit for K is molarity over seconds. So I've thrown a lot of information at you, huh? Don't freak out if it doesn't all make complete sense yet. We're going to work through a few problems that could appear in your test, and working these problems should get all the info in order for you. What are the units of the rate constant K in the following rate law? Rate equals K times the concentration of X times the concentration of Y. So the unit we want to get is moles per liter over seconds. The unit we have with the concentrations is moles per liter squared, because it is second order overall reaction. So we need to get rid of the 1 mole per liter and add on a 1 over seconds. So our answer is B. The rate law for the reaction shown is the following. What is the overall order of the reaction? So the overall order of a reaction is the sum of the exponents of that rate law. Two exponents on this rate law are 2 and 1. So when we add these two, we get 3. Therefore, the answer is B. Consider the hypothetical reaction below. It is found that doubling the initial concentration of A causes the initial reaction rate to be 4 times as great, and tripling the initial concentration of B causes the initial reaction rate to be 3 times as great. What is the overall order of this reaction? So first let's look at A. It says that when you double the concentration of A, then the rate is times 4. The square of 2 is 4. That means that A must be a second order reaction. Then there's B. When you triple B, the same thing happens to the rate, which means that they are directly proportional, and therefore B is a first order reaction. So then we look at the rate, knowing that the order of A is 2 and B is 1, which means our exponents are 1 and 2. We add these together to get 3. Therefore, the overall rate of a reaction is 3, and our answer is C. Given the initial rate for the reaction, determine the rate equation for the reaction. So this one is a little more tricky, but if we take it slow, it won't be too bad. So when you see this problem, the first thing you should think is that the last column rate appearance of C is going to be your rate in your rate law. So you can think of our rate law being C, or the last column equals K times the concentration of A times the concentration of B, where B and A will have their needed exponents. So to do this, we need to look at when the concentration of A changes but B doesn't, since we only want to mess with one thing at a time. This happens on the first and third row, so let's look at those individually compared to what the rate value or the third column is at these points. We notice that on our concentration of A, we get that the second value is 3 times the first. Then with the rate, we get that the second value is 9 times the first. So now compare the number 3 to 9. We know that the square of 3 is 9. The only time that the number you multiply the rate times is squared of the number you multiplied by the concentration is in a second order, because it has the squared value in it. Therefore, A is a second order. Now we take a look at B. When we look at B when A is the same, and this happens in the first and second row. We also look at C at this point. We notice that on both columns, to get from the first number to the second, you multiply by 2. The change in concentration, therefore, is directly proportional to the change in the rate. The order that follows this rule is the first order. So B is a first order. So we have a second order in A and a first order in B. The only one that fits this choice is choice C. Well, now I have definitely loaded you down with a ton of information. So before we part ways for good, here's just showing you some of the key things we covered. Hope you have a great day and good luck on